GM, what's up? Welcome to Web3 Club, and in today's video, what we are going to discuss is how do we use Merkle Tree as a proof for allow listing or whitelisting somebody's address so that they can and only they can mint something off your smart contract. I've already done a previous video on whitelisting, allow listing, gasless allow listing, which I think somebody is linked somewhere above. There we were trusting a private key to sort of sign messages for allow listing. But here we will not do anything like that. We will just use pure plain cryptography and make a proof so that nobody can fudge with it, even if they get hold of any sort of private keys. Unless, of course, they become the owner of the smart contract. In that case, they can change the Merkle tree root. But before we get started, please make sure to hit that like button, subscribe to the channel. If you have any questions, please leave it in the comments or come hop onto my Discord server. There are a lot of people just like you who are helping each other out for with any questions that you can have, and I also try to chime in every now and then. Alright, with that said, let's get started. So as per my usual modus operandi, I'm on the wizard, Open Zeppelin wizard, and I've created a small NFT contract that I will open in Remix. Let me just zoom in so that you can see the code a little better. Alright, so this is a very standard contract where there is no limit, there is no upper limit of minting. What I want to do is only want to allow a certain set of users to mint these tokens. Now, I'm not going to build a complete full-fledged NFT smart contract. I've already done that multiple times in my previous videos. So if that is something that you want to build out first, just go check out those videos and then come here for the whitelist, allow list part. But before we do anything, let's just discuss what is a Merkle tree and how do we use it for creating a whitelist or an allow list. So I've opened a Merkle Tree JS npm repository over here, and here you can see what the tree sort of looks like. So there are elements that are present which we run through a function, a hashing function. We get a leaf of this tree. So every value that we have, we run through a hashing function and we get a leaf out of it. After that, what we do is we take the two leaves and we run them through the same hashing function, and we get another leaf sort of the branch, and we keep doing that on every level to finally get a root. So what we will do is we will use ksec2256, which is a common hashing function used in Ethereum. And what we will do is we will use addresses as values, and we will run ksec256 on those addresses, generate the leaves, and with the leaves we will generate a root at the end. After that, we will put this root value into our smart contract, and we will write the Merkle tree generation code directly in the smart contract. So what smart contract will then require is the leaf and the corresponding leaf and the corresponding path to the root. So if this is the address that we want to verify, what we will do is we will send to the smart contract this value and this value, and then this value, and then this value, and then the root, of course. So what smart contract will do is generate a hash. This is the hash that the smart contract gets. Then it will generate a hash again, and this is the one it will get. And then because this is also the one that we had sent, so these two will generate this one, and then we will send this, actually not this. So this and this will then give us this. If it is a little confusing, just go through this part 2 or 3 times because it's very simple. It's not that difficult. Basically, if we know the path, we will just send the next child, the cousin, the I don't know what to call it, but the next child of that path, so that the smart contract then can then figure out what is the root that is being sent from this. So what happens is if we change any value by any small amount, the root sort of changes. So you will not get the same value if the value was not present in the actual allow list. So this is how sort of Merkle trees work in general. What we will do is in the smart contract, we will only implement the hashing of from the leaf to this thing to the root, instead of sending the whole allow list every time somebody's trying to mint. We will just send the path that we want them to take. This works very efficiently as well. It takes O log of n time, if you know what that means. Is it more efficient than signing a message. I'm not really sure, but I think signing a message will be more efficient because it requires less computation. And as always, OpenZeppelin has a Merkle proof.sol library available for us to use, which gives us a very nifty verify method that we can use in our contract. So what I'm going to do is I'm going to import this file. So to import that, I can see that it is OpenZeppelin contracts, utils, cryptography, Merkle proof dot sol. So I'm just gonna copy this, import over here like this. So I'm going to add at over here, then contracts. I don't need this. I can add at 4.5.0 just to make sure that nothing goes wrong. And yeah, this is the URL that I will need to import. OpenZeppelin / contracts at 4.5.0 utils cryptography merkleproof.sol. Great. And the function, another function that we will write over here is called is valid, which will take the bytes 32 memory proof. This is the proof that we send for the path to the root. So this is the proof that we will send, and we will also send the leaf because root is something that we will store ourselves. So these are the two things that we will send. I'm making this a function, making this function public so that we can test out whether it is working or not. In practice, you can make it private as well. It returns a bool, and it's a view function. It doesn't really change anything. And what we will need to do is call Merkle proof dot verify with proof, a root, and a leaf. And now we haven't stored the root anywhere, which will be a bytes 32 value. So what I'm going to do is write bytes 32 public root. All right, and this is the value that will come from the constructor. So here we will be writing root equals to underscore root. All right. Now, before the safe mint, what you will do is you will have your own require statements, which will limit, let's say, 10,000 or whatever. And in there, you will also add a require called is valid. And these are the values that you will sort of need from the safe mint function. So the values that you will need are bytes, memory, proof, and bytes 32 leaf. And in the is valid function, you will send these values proof and leaf, and if it is not valid, you just write not a part of Allowlist. Okay, so now we will not be able to mint if you're not part of the Allowlist. This is all that we need from the smart contract side. Of course, you will add other require statements, but I'm leaving that to you. We can go ahead and compile the contract, and there's an error already, which is that I haven't added the semicolon and another semicolon. And another error that is that bytes 32 needs to be an array. And another thing that I forgot is add a return statement. My goodness. All right, so this time it compiled successfully. We can go ahead and kind of deploy the token, but it will need a constructor value, a root. All right, so I don't have that root. So now let's go ahead and create that root. So to do that, what I'm going to do is create a new folder called Merkle Tree, and in that folder I'm going to create an index.html file. Open it in Sublime Text, and in the index.html file, let me just start the HTML stuff. Now the first thing that I need to do is import Merkle Tree.js. Now if you're using a sophisticated project, you can just write npm install, but I'm going to do it via browser. So I'm just going to include the script, the CDN file that Merkle Tree.js has given me. Another thing that I will need is ksec 256 that again I will take from the CDN, otherwise you can do it via npm install. Now another thing that I've done is generated a few addresses and added my address to the end so that we can generate an allow list using these addresses. So let me just format these addresses so that they can generate, and we can generate an array out of. All right, so now we come to our HTML part. In the script we have an array of addresses. Now the next thing that we will want to do is generate leaves from these addresses. So what I'm going to do is I'm going to write const leaves equals addresses dot map, and in the map what we want to do is run ksec 256 for each of the addresses. So this way we will generate the leaves from these addresses, and remember I told you to sort of generate these leaves by running a hashing function. So that is what we are basically doing over here, and once that is done, what we can do is generate our Merkle tree as well. To generate the Merkle tree, we can just copy this and paste it over here. Instead of SHA-256, we need ksec-256. And another thing that we will need over here is a little tricky for you to understand, but basically in the OpenZeppelin's code, OpenZeppelin's Merkle tree code, you can see that here it says the pairs of leaves and pre-images are assumed to be sorted. So we will need to sort these, and for that what we can do is add an option over here which will be sort pairs true. So this is how you generate a tree. Now another handy function that we will sort of need is buff to hex, which means buffer to hexadecimal. We will just add 0x over here and then x to string. All right, and then this also has to have like this also needs to be a function like this. So now we will get a tree, and to get the root, what we need to do is just console.log tree.get root. All right, so I'm very excited to try this out. What I'm going to do is I'm going to http server, and yeah, and then I'm going to open localhost port 8000, and if I open the console, I will see some value over here. Right, so this is actually a buffer that I need to sort of change to hexadecimal. So I'll just write buff to hex over here and close the bracket and refresh. Okay, I'm getting a weird value because I didn't specify it to stringify via hexadecimal. So now I refresh again, and this time we get a hexadecimal out of it. So now we can just simply add this value over here, the value that I copied, the root, and then deploy this smart contract. All right, so I click on transact, and the transaction has gone through. Now we have this function called isValid, and how do we use it, right? So we need to sort of send some bytes, an array of bytes over here and a leaf over here. So now let's say I want to generate the leaf. I have the leaves, right? So I want the leaves of probably the last one, which would be, I guess, 38. Yeah, what I can do is buff to hex. All right, and this will give me an address, I guess. Actually this gives me a ksec value of an address. So what I can do is actually call addresses, and then there I can find out the 38th one, which is my address. I can do a ksec 256 of that address, and if I do buff to hex of that ksec value, I get this value that I had earlier gotten. All right, so this is the leaf for my address. So if I want to send my address for minting, what I will do is generate this leaf first and then send it out. Now there is a small bug in the code that we have written, and that bug is basically that anyone who has these proof and leaves will be able to mint, because we are not making sure that the leaf belongs to the sender, belongs to whoever is sending that value. So another part that I think we should sort of add over here is that the leaf, the value of the leaf should be equal to the ksec value of the message sender. So to do that, what we can do is add another require over here, and we can just be like ksec 256 of message.sender is equal to the leaf. Another thing that I forgot to do over here is abi.encode packed and then message.sender. sender. So hopefully this should work. Great. And this is how you can basically generate it. Another thing that you won't then need to do is, you don't need to accept the leaf, right? So instead of leaf, what you can do is, in the is valid proof, you can just send the kasek value. Great. So I can compile the contract again, and this time again it should compile for no reason. What I'm going to do is I'm going to remove the old deployed contract, and I'm going to deploy the new one again with the correct root. Okay, so I'm going to transact and it has deployed. Now how do we figure out the proof and the leaf, right? So leaf, we already know we can do a kesek to figure out the leaf. So this is the leaf for my address. Okay, and now I need to figure out the proof. And to do that, Merkle Tree has a very simple thing called tree.getProof. So I'm just going to write tree.getProof for a leaf which is not defined. So the leaf will be kasek 256 of my address, and this is the proof that I have received. The next thing that I want is, from this proof, I want to map out only the data, and even in the data what I want is buff to hex this data, so that I can get a value which looks like this. Okay, and I can just paste it over here. Make sure that there are no white spaces or enters or anything like that. Like I can see a whitelist over here, white space over here. Okay, so this is our proof. So I'm going to go here in the isValid function and enter this proof, and I'm going to copy the leaf and enter the leaf here. Now this should return a true value, which it did. And why did it do that? Because our address was part of this, right? Now assume that I also have another address that is not part of this. If I copy that and if I try to generate the leaf through that, I will get an error. And let me just generate the leaf. So I'm generating the leaf, and this is the leaf that I got. And if I try to paste this leaf, right, this will return false. And if somebody else tries to sort of mint it, it will give an error. Now there's a problem with my code because I've done only owner over here, not the right thing to do. So only owner can sort of mint it. So what I'm going to do is I'm going to remove this only owner part, and I'm going to remove the transaction, the contract again, compile it again, and then deploy it again with the proof that we have. Okay, so now if I try to safe mint from whatever address, right, if that address is not part of the Merkle list, it will not work. And I can just try it out. I can use the old path that I had generated and click on transact, and you can see that there is an error. Now how do I make sure that it sort of goes through? For that, what I need to do is add this address or any other address to the Merkle list, to the Allowlist, to the Whitelist, to whatever you want to call it, and generate this root again. And the next time what I can do is, I don't think I have a method to change the root, so that is something that you can add, but otherwise I can remove the contract and generate a new one with the new proof. All right, and this time with this specific address, I can generate the leaf. The leaf will be kasek 256 with that specific address, right? And from the leaf I can get the path. To get the path, I can get the proof, right? And for the proof, I can just enter the leaf over here, and this will sort of give me a proof that then I can map out to give me buff to hex of x dot data. This is the final proof that I will receive. Great. And for this proof, what I can do is remove all sorts of spaces. All right, so I can make sure that there are no spaces left by command F space, and there is none. So I can copy this, and I can go to safe mint this time and enter the proof and enter my own address, because why not? Click transact and it works. So this is how you sort of add a list. Right now, how do I do this via JavaScript? This is, we are doing in a very weird way, right? So I'm going to create copy this and just sort of paste this over here. This sort of gives us our proof, and for the leaf what we need is kasek 256 and whatever is the user's address. So if you are just using the way I normally do, you will have some sort of address present, right? So you can just add that address over here. So this is how you will get the proof, right? And then what you will do is you will call contract dot, let's say, contract dot methods dot safemint, and in the safemint you will add the proof to and proof, right? So to will be the address of the user and proof, and then you will sort of send this with whatever from address. All right, so you can figure out the address from the wallet using wallet connect slash metamask. All right, and once you create that address, you can get the leaf, you can get the proof, and you can go and call the safe mint method. All right, so this is how you will sort of allow user to use Merkle list to get on a Allowlist whitelist, Merkle tree actually, not Merkle list, and allow them to mint through your contract. This specific method will be called on click of the mint button. All right, so I'll share this code in the GitHub gist, and I will link to it in the description down below. And that's it for the today's video. I hope this was helpful. I have another video which explains how to do a whitelist through signing messages. Make sure that you check that out as well, because I think that takes lower gas for minting than this. In any case, gasless whitelist allow list, it means that you as the contract owner don't need to pay for gas, a bunch of gas, to add somebody to the whitelist, right? To add somebody to the allow list. The thing with the signing method is that you can do that off the smart contract, but it sort of leaves a vulnerable position where, if your private key is compromised, anybody can get on that list. This sort of makes it permanent, like it's present in the smart contract that only this Merkle root is allowed to mint. The problem with this is if you want to change the list, you will have to change the Merkle root again. So just something to keep in mind. And this will take a little more gas for the users to mint compared to that. But anyway, I hope today's video was useful. If you like this video, please make sure to hit that like button, subscribe to the channel if you're new. If you have any questions, please join the Discord. There are a bunch of people who are helping each other out. Even I try to chime in there once in a while. Leave a comment. I try to read most of them. I don't get a lot of time, unfortunately. But yeah, hope this video was helpful. I plan to see you again next week. Thank you. Bye bye.